Hello. So my initial title was F-theory and G-flux. Now I realize that there are lots of talks on the subject of G-fluxes. Now the conference is really called String Phenomenology, and there hasn't been too much on the actual phenomenology of F-theory, etc. And since we've done some work on that, I decided to slightly, put an emphasis on this phenomenology and insert basically half of my talk to be a phenomenological sort of study of what F-theory can do, can't do, and what we've learned so far. And this is a work in progress, together with the usual suspects, Joe Marsano, Natalia Salina, and also Matt Dolan, who is a phenomenologist from Durham, and two students, Moritz Künzler, who is here, and Craig Laurie at King's. Okay, so the plan is therefore two sort of parts. The first part will be a sort of story on F-theory phenomenology. Now, the first conversation I had when I arrived here on Wednesday was a lot of the talks at this conference are very sort of on the level of preaching your own model to everybody else and convincing everybody that it is the best model. So what I really don't want to do this, so the main goal here will be less of a sort of indoctrination, more of a pointing out some things that we have so far not incorporated into the study of F-theory model building. Actually, this just broke down. Okay. So it's more like pointing out the annoying features that we have, and which I think should be fixed in some way or another and addressed, I think, in the future in order to really have sort of not fiction, but actually facts that you can present and say, okay, this is phenomenology that really is based on an F-theory model, and other things are not. And to be really sharp about this. And the second part is then some F-theory G-flux geometry that I initially planned to talk about, but I'm sure that Timo and Thomas already did that, and also Miriam mentioned it. This is, sorry. The guy in the box. Let's see. I will try not to move too much. Okay, so let's start. F-theory phenomenology. We've heard this many times. Let me start again at the beginning. We're talking about F-theory. Type 2b, we allow the axial dilaton to vary. We geometrize it compatible with the SL2Z action. And so in order to get 4D n equals 1 vacua, we're actually looking at elliptically fibered Calabi-Yau fourfolds over some base manifold B3. There's a real 6-dimensional manifold, and E tau is elliptic curve. And then we have the usual story by now, how we actually engineer SU5 gut models. So most of the gut model building is really based on this minimal kind of gut construction based on these papers. So the sort of geometric way to address this is we're looking at singular elliptic fibrations. In codimension 1, the fibers are known to be all of ADE type. And so what we have is this torus sort of moves along this base manifold, and then at some points becomes singular. And if we can describe it in terms of Weierstrass form, we have a very precise notion of when it actually becomes singular, namely the discriminant, this combination of these sections f and g, which are functions varying of this base, will vanish. And so our gut group, or our gut stack of 7 branes, will actually be wrapping this as gut, which is a component of the discriminant, times the flight R3,1. And then we have this nice sort of usual picture. We have intersecting branes. Those are realized in terms of two of these loci of enhanced singularity coming together, forming sort of matter curve. This is this green thing. And then Yukawas are generated from the intersections of these matter curves. But we can, of course, put this all into a nice mathematical framework, which is really the power of this F-theoretic approach. Namely, if we have, say, an SU5 along S gut has a local coordinate z that vanishes there, then the discriminant has some vanishing order z to the 5th. And then some nice theorems tell you, then actually you don't have to work with this general Weierstrass form, but you can automatically put this into the so-called Tate form globally, which takes the form of this kind of equation. where the vanishing order and z of these coefficients essentially tell you what type of singularity you have. And this is sort of a very nice starting point, I think, for most of the gut model building endeavors that address anything that is global. Okay, so from this Tate form, now we can see all these pictures, how they emerge, right? So how all this matter stuff and the Yukawas emerge. In codimension 1, z equals to 0, we get an A4 singularity. That is precisely how we engineered it. That's by construction. Codimension 2, we get matter, and that's localized along various loci, which sort of in a naive terminology are called the SU6 and the SO10, loci of enhanced symmetry. So I'll get to this point later on. That is a little bit of a misnomer. There really isn't a local SU6 or SO10 gauge symmetry living there. There's something very specific that happens in the fibers of the Calabi-Yau. But for now, I'll just refer to this as the codimension 2 enhanced loci of symmetry. And similarly, Yukawa couplings arise, as we heard, from these SO12 and E6 points, top Yukawa and bottom Yukawa coupling. Okay, so this is the basic setup. And now to actually get to some physics, we take a local limit. So I'm going a little bit backwards now. So now I have this Calabi-Yau, their brains wrapping, and I'm zooming into where the S-gut surface lives. And locally, the structure of the singularity is actually a very nice, simple thing that we've heard now a couple of times already, also in the last talk. It's something that looks like in the 8th singularity that's been unfolded to an SU5. And as you now set some of these sections now on S-gut to 0, you get the various matter and Yukawa couplings. Now the data that's really encoded in this local geometry is completely equivalent to the data of this E8 gauge theory Higgs to SU5 with adjoint events, or put differently, these coefficients alpha that we get from restricting the coefficients in the Tate form to S-gut parameterize a Higgs field and a so-called Higgs bundle data for a theory that lives just on this gut surface. Okay, so this is the basic setup. Now, locally, there's a lot of engineering work that you have to do. So you have to, for example, first of all, package all the geometric data and the G-flux that you would like to have in a global model into this language of Higgs bundle spectral cover and line bundle over this spectral cover. And that's sort of one part of the work where you really just engineer all the matter, the Yukawa couplings from such a spectral cover. Then, slightly more upsettingly, the way we're breaking the gut symmetry is with this hypercharged flux that will cause a lot of issues in what follows. The hypercharged flux is breaking the 24 of SU5 to the adjoints of the 3-to-1 gauge groups of the MSSM, and you get then these extra XY bosons, which you have to lift. And the hypercharged flux is engineered such that it lifts those exotics and also the Higgs triplets. But it does it as a cost, and it's debatable whether this is at this moment the best way to go forward. But it's a very nice general sort of setup that you can then study, and I'll show that it has some nice predictive power. Okay, and then the last point is proton decay prevented by a PQ symmetry. PQ symmetry for all purposes just means the Higgs up and Higgs down have not opposite charge. So there's no coupling like the mu term, Higgs up, Higgs down. This will actually then automatically also prevent the Q cubed L operator that is the dimension 5 proton decay operator. Okay, so these two couplings are then absent once you have engineered something in this local framework that has a PQ symmetry. And the way it is done is, just sort of briefly to summarize, you have to actually look at this spectral cover, and the additional U1 symmetry arises by factoring the spectral cover. Okay. Now, this seems like a completely reasonable sort of set of ingredients that you put in. You can ask, can I now build actually a minimal SU5 model from this? What it actually turns out is just having this hypercharged flux plus an additional U1 symmetry, you get a very simple condition first noted by Dudas and Palti, and then shown by Joe Marzano to be coming from really anomaly cancellation of mixed U1 and MSSM anomalies. It says that you cannot distribute U1 charges, these QIs, and QAs on the matter curves arbitrarily, there's actually a relation that has to be satisfied with the hypercharged flux, the restriction of it to the matter curve, and the charge of the matter field that lives on the matter curve. So this relation always has to be satisfied. It seems like a very simple relation, but then actually when you look at the consequences, what they're saying is if you have a minimal SU5, you don't want any other states, then the only compatible U1 is a U1 essentially B minus L. And that is definitely not a PQ symmetry, namely it will not prevent these couplings that we had here. If you would like a PQ symmetry, so then you get contributions in particular from the Higgs up, Higgs down, having not opposite charges, so they give a non-trivial contribution to this equation that have to be cancelled. Then you automatically, from this relation here, get non-gut exotics in your spectrum in order to just cancel this relation. So the upshot is you would like to have a PQ symmetry because you would like to fix proton decay mu term with a U1 symmetry. Then you also have hypercharged flux gut breaking. Then you will automatically get these additional states in your spectrum. Okay, so this is sort of one simple corollary of this. In particular, if you would like to have this kind of setup, you will not get a minimal SU5 model as you might have thought locally. Okay, so then this is the punchline. If you have no mu term, no dimension 5 photon decay, you have U1 PQ, then you get these exotic fields. And the exotics are really labeled in terms of integers, and M is, if you just set N and L to 0, you just get the standard 10, 10, 5, 10, 10 bar, 5, 5 bar kind of matter content. So N and L really measure the difference of the restrictions of the hypercharged flux. So this is what's encoded here. If the charge of the Higgs up and Higgs down don't add up to 0, then this is a non-zero sort of contribution that will sort of change the spectrum, and you'll get really different numbers of 1, singlets, 3, 2s, 3 bar 1s, etc.
But this is vectorized, right? So they can get large mass somehow?
Yeah, but you will have to explain whether. So what we'll get at is actually you can either do that, or you can use them in a different way so that they actually have a nice phenomenological implication. But we'll get to this in a second. Okay, so then, since we're at this moment in sort of on the engineering territory, you can ask, okay, we had a couple of assumptions that go into this framework. You can relax that, for example, include discrete symmetries. That's always a non-generic kind of thing, right? You need a Calabi-Yau with a base that has some Z2 action or something. So that will be a sort of more model-by-model dependent approach. Similarly, Wilson line breaking will probably not be generic, like there was a paper today by Stewart and company studying this. So there are indeed solutions around this where you're not using hypercharged flux, but they're again very sort of example-based. And then, so I think the most interesting option to get around this is, so I think was pointed out in the paper to Nagy and Reinhold on the gluing branes, you could put the Higgses into the bulk and study models that prevent couplings because stuff can actually live in the bulk of its gut rather than just on matter curves. But I think that's sort of something that hasn't been developed, but I think has a potential to be on the general sort of footing. We have a generic kind of conclusion here. Similarly, I think you could draw something there. But then, as you were just asking, so what do you do actually with these exotics? So you have a non-minimality. You could say it's a bad thing, but it could also be a good thing. So one question is, do they have any signature at all? Or they have any interest in the phenomenology? After all, we're trying to not just build models for our own satisfaction, but actually trying to build something that maybe has some effect as to what we'll see at the LHC. So utilizing these exotics as messengers in gauge mediation is actually one way that you can sort of get some interesting signatures out of these models. And at this point, I really would like to emphasize this is not just one model that you pick, and the model corresponds to a specific Calabi-Yau. And if you change the Calabi-Yau, it'll change drastically. What happens here is really you only have the inputs U1 PQ symmetry, hypercharged gut breaking, and then the matter lives on matter curves. Then you get this kind of exotic spectrum. So in particular, if you use these vector-like non-gut exotics as messengers, one thing that changes directly is the standard genome mass relations M1, M2, M3. They are changed by these integers, which are really the flux numbers, the restrictions from the hypercharged flux. They change from the standard 1 to 6 to something that depends on these coefficients. So then you can ask, all right, is this of any kind of phenomenological use? So what we did is we started with a very simple model. Again, you could criticize this because we haven't explained how you actually break supersymmetry in some hidden sector, etc. But assuming you have a simple superpotential with a F term, X develops an F term here, and you have a coupling of the singlet X to the messengers, so F and F bar are these exotics, and these then talk to the SU5 gun via the gauge interactions, and you have a U1 PQ symmetry under which this singlet is charged, and the Higgses have non-vanishing sum of charges. Then you can sort of write down this kind of standard sweet spot supersymmetry model where you have a relatively high gauge-mediated setup. So Fx is mostly of the order of around 10 to the 19 GeV. The mu term is generated dynamically from the coupling X HH bar, which is allowed, and mu is sort of generated reasonably accurately. But the gravitational mass sits really at the boundary of what is allowed for gauge mediations, about 1 GeV. Okay, so as I said already, the gaugeino masses will change by these beta function coefficients, which are now altered due to these additional multiplets that we have, and also the scalar two-loop masses get contributions from that. But we'll see that actually the gaugeino mass changes are really something that you could make quantitative use in LHC studies. Okay, so these ratios change. Then we looked at what we did together with Matt Dolan and Joe, is to look at benchmark models for various fluxes, and then crucially compare that to something that's like a minimal gauge mediation model. So the minimal model would have 5 bar, in this case 3 of these 5 bar messengers, and all the other ones have, as you see, these L's are all switched on. And then just scanning through the space of these flux choices, we get reasonably high gluino masses for these models. If we just focus on, say, one of these, you can scan through all the allowed values of tan beta and also the Higgs masses. So if you look here, so 126 is right at the boundary. Right, so lambda is Fx over the messenger mass. This is the messenger mass scanned from 10 to the 13 to about 10 to the 15. But there's indeed sort of a band where you're precisely at the 125, 126 range. This was sort of, we published this before December, so it wasn't sort of put in or anything. It's just, this is the range of masses that you can get in these models. The black thing is sort of this left bound that you definitely have to be above, but at the higher end of Fx over ms, you could really have some models that potentially are interesting. Okay, I'm just showing this. This is sort of the class of models that would come out from here. Now the comparison is the interesting thing. This is now a minimal gauge mediation model with a similar comparable gluino mass. This is here. I don't know whether you can see that. So comparable around 1.4 TeV. And what we looked at is just where do the spectra sort of have distinct differences. And as expected, sort of the Chargino-Neutralino sector is the thing that is sort of squashed or expanded depending on what these flux choices are. So here you see this is particularly sort of differently spaced from the models that you would get from minimal gauge mediation. And of course you can say, okay, that's one model. Is there something you could really put in quantitatively and say, we measure this kind of model, can we rule out that it's really this type of model? So there's some nice sort of way you can do this. So people actually here in Cambridge, they've sort of developed Oh, 10 minutes, okay. So it'll be just a phenomenology talk. Yeah, you can listen to Timo for the G-flux. So these models have very similar features. They have large tan beta. If you look at the values that we're scanning through here from 30 to 50, the spectra are similar. The production cross sections, which I didn't show you, but they're also very comparable. But there's one way you can really sort of nail down the difference in this, what I showed you, this gauge genome mass relation, that's crucially different, is if you look at this decay left and its quarks into eventually a neutralino and some leptons and quarks. So this is some ratio that essentially measures the difference between the first and second neutralino. And if you look at the spectra, they're sort of spaced like here, and here they're spaced like that. So these are really these are so-called kinetic invariants, which are, for our purposes, I think, just measuring how the neutralino 1, neutralino 2 actually differ. And in a given model with a fixed gluino mass, how would you actually distinguish models with different splits between those two? Then this is the quantity that you can actually look at the data. And if you compare the minimal model with the model that's this benchmark model, indeed, this is quite a substantial thing that you could actually go out and look at and really see. Okay, so this is just to illustrate, these models may not be something that you would look at, just out of your own doing without looking at F-theory. Once you are motivated to look at these non-God exotic gauge-mediated scenarios, then you're actually brought into this regime where you could distinguish them into, from the minimal gauge mediation models. Okay, so this was just this was sort of to illustrate F-theory is in some way. If you want to put in a framework, you say you're looking at gauge mediation, you're looking at non-God exotics, therefore, then it is relatively predictive. The question is just, is this really something that is reasonable to expect that gauge mediation is the thing that is realized? So this is what I wanted to call the point of annoyance. Then in all of this, we always assume, and I think from the very beginning in this F-theory literature, we've assumed gauge mediation is natural. We would decoupling gravity. We could just, live in this world of gauge theoretic things. So it seems natural, at least in the local model. In there, I think it even seems natural to just look at vanilla minimal gauge mediation. Certainly in these sort of constructions that I just showed, it's natural to look at gauge mediation with PQ symmetry, and it's very robustly constraining the outcome of these models. But it totally misses, I think, the point that maybe these contributions may be super subleading and totally not important, right? It's a nice thing that they're out there, and they could be nice signatures, but we're completely ignoring the fact, and in all of this, we're really choosing by hand the value of this M3 halves, right? So we're just saying, okay, this looks natural, but actually there's no reason why this should be the case. So in all this, we assume M3 halves is sort of lower, bigger or lower, is much smaller than 1 GeV. Maybe it goes up all the way to 1 GeV, but then really we're saying there's nothing above. All the contributions above that are completely negligible. And that gives nice signatures, but it could be, indeed, there are lots of other issues. And I think one particularly interesting thing to, maybe in F-theory to think about is, what about this moduli issue? So you two have, yes? It's order 10, no? TV, sorry. No. Order 10, even if it's 10 GeV, it would be horrible for these models. But 10 TeV is even more sort of drastic. So the problem is here, there'll be light moduli that can screw up your cosmology. There's, as far as I can see from the argument that you guys are giving, this is sort of generally applicable. It would be, I think, very naive in F-theory to just ignore these kind of things and just go out and say it's, for all purposes, gauge mediation. So I think that's a very sort of crucial point to address in the future, and to see, is there sort of a balance between these? are there setups in F theory that, either say, these contributions are not there, we have a different way to solve these problems, or if these are applicable arguments, then the question is, is there still something left that is very characteristic F theoretic? So what we saw in this gauge-mediated setup is, yes, there is stuff that's really completely something you wouldn't look at normally, but in these other kinds of models, it would be interesting to understand what is happening. So this is the thing that really upsets me, that we've been always, it's sort of also a criticism of really the whole sort of direction of research. We have never addressed this question. I think that's something that we should look into. Okay, so in 5 minutes, geometry and fluxes. I think one thing that I'd like to point out in here is, maybe not the G flux, but the first point. So the whole study of these global models really, I think, sort of kicked off with the work of Isol and Yao last summer, where they looked at the resolution of SU5 singularities and looked at global Calabi-Yau fourfolds, where you do the resolution, find the structure of the codimension 1, codimension 2, codimension 3 fibers. What's a little disappointing here is that the math literature is very scarce on results on higher codimension singularities. And it would be extremely interesting to further understand what is happening there. So, so what Isol and Yao did is really pick this Tate form for the singularity and resolve it, find exceptional divisors, and show indeed in the fiber you get an A4 type or an affine A4 type singular structure. So after the resolution, you get really a smooth fourfold. You have divisors that intersect in an A4 affine extended Dinkin diagram. So that is sort of something that is intuitively clear. What was less clear at the time when they came out with the paper was how the Yukawa points and the matter enhancement loci work. Because what happens, and it's sort of really along the lines of saying that no one really guarantees you that there'll be Kodaira-like fibers in higher codimension, what they found is indeed the fibers are not Kodaira. And in particular, there's no such thing as, for example, an E6 fiber sitting on a point of E6 enhancement. So what we actually then realized is, indeed, this is not a problem with the physics, it's just that what is happening is slightly more subtle than just looking at some fiber structure degenerated to a higher ranked age group, a Dinkin diagram, and then et cetera, et cetera. So actually what is happening is in codimension 2 is that the Dinkin diagram, all the roots of the A4, partially split into weights of the SU5 and roots. So some of these remain irreducible, and some actually split into weights. Now the total number of these is indeed compatible with a so-called SU5 or SU6 or SO10 enhancement. However, what is happening is not the intersection of these fiber classes is actually not giving you an SO10 or SU6 fiber structure. So you get the right number of additional degrees of freedom, but you don't get what you naively would have expected, an enhanced gauge symmetry of higher rank. Similarly, in codimension 3, this is something that's even sort of less from the point of view. I think I still have 4 minutes, no? Because it's until, no.
An hour.
No, it's 35 minutes.
No, after the questions.
Oh, okay. Maybe there are no questions. We will negotiate it. So at the codimension 3 locus, what you have naively thought is there's an E6 fiber sitting on a point or an SO12 fiber. What actually is happening is some of these classes correspond to, for example, this weight corresponds to an SU, the enhancement from here is one of the weights here, from the SU6 enhancement, splits and becomes homologous to two of the weights that come from the SO10 splitting. So actually, the geometric picture is not, as I move to the special point of E6 enhancement, the fiber becomes an E6 fiber. What actually is happening is the three curves meet together and become homologous at that point. So there's really only, so you can think of it as like a 3-chain connecting these curves, and then at the points when these coefficients correspond to, say, the E6 locus, they actually become homologous. So in this sense, I think it's actually an interesting question to understand when we all think about E8 points going even further, how that would actually geometrically arise, right? This is slightly unclear from this point of view, how all these things would actually merge and, you know, give rise to, you know, equivalence of classes that would correspond to an E8 point. Anyway, so this is the upshot. I think there's something more to be done in the you know, direction of understanding how the fibers work in this higher codimension. If you look at the intersections, they're clearly not just ADE fibers, so some classification of these definitely is sort of necessary. So the flux part we will hear in the next talk, I guess. Just a few comments, generalizations. These you know, splittings, etc. That's a very general story that doesn't rely on SU5. You can study this, in fact, for all the singularities that you can find in the Tate table. And in fact, so let me just, since you say 1 minute, so the upshot is what you're looking at is geometric engineering of these dot models with Martin-Yukawa couplings. Phenomenologically, we can make a lot of sort of progress, making very mild, I think, assumptions about what we're putting into the models. And to start with, we get some interesting results, you know, that could potentially be interesting for the LHC. However, we are really completely ignoring some issues that could just, you know, wash out all these effects that are, you know, standing out there. So that's something that I think should be addressed, in particular in the context of these papers by Bobby and Gordy et al. Okay, and then geometrically, as I said, the higher codimension singularities should be interesting to be studied in some more detail. What I didn't say is, you know, phenomenologically we had all these U1s, the PQ symmetry was crucial here. Global models that have a PQ U1 symmetry have, I think, as far as I know, not been constructed yet. So far only these so-called 4+1 models have been constructed. That's definitely something that has to be done, as otherwise we really don't have sort of a globally consistent model that would correspond to a PQ U1 symmetry. So this is something that I think is also up for, you know, someone to work on. Okay, so let me finish and thank you for your attention.
Very interesting.
Yes, come on.
Questions?
So just a comment about the cosmological issues that you mentioned. In the context of the gauge mediation, one scenario was proposed in the context of F-theory in my paper with Tawan, Farah, and Hickman, where a late decaying Saxion gets rid of the issue of this overproduction. So that, and in fact, in our context, that was very natural.
Yes,
That's one
but the
comment.
model that you studied, I think, had got messengers, yes? There was, I think that was in the context of a PQ model, yes? That was, yeah, so you have PQ, you want symmetry, and you assume they got messengers.
Yes,
And I don't think that model is realizable.
certainly is realizable, but
Well,
there's no problem with that model.
We had long discussions with
But that's one comment. The second one is that these structures that you're mentioning about symmetries not being realized at singularities is related to T-brane structure that was mentioned.
Yeah, I see.
That's
Yeah.
because in the example I showed the monodromy, when you have monodromy, for example, for SU2, you get square root of x and minus square root of x. At x equals 0, you would say it's SU2. But that's actually not what happens. It's actually 0, 1, x0.
Yeah.
At x equals 0, you don't have SU2 symmetry. So
Right.
the structure of the breaking and all that follows as if it were. So that follows from T-brane structure.
Right,
So it's
okay.
not a mystery, in other words.
No, it's not a mystery, but it was, you know, the geometry is
The
not.
word was, I think if you take it literally, the word that's a singularity would be a mistake. But
It's not.
But the
That's
jump, but what is true is that in the particular E6 gauge group,
Yes.
there's a configuration which at the origin
I see.
does not restore E6, but still inside the E6 gauge symmetry.
Yeah,
So in that sense,
that's-
it is
that
E6.
makes all the sense.
David?
I have a question. The mu term was related to the Tate-Quinn symmetry,
Yeah, it
right?
was.
So if you add a mu term to the MSSM, how do you actually solve the strong CP problem? Because then,
No, this is not. So the PQ in this context is, at least for this purpose, completely coupled from that question. It only means, think of it just as a U1 symmetry defined as just having this property.
but
It-
you
it-
solve the strong
No,
CP
we're not
problem.
even, I think Kumran may have addressed this in some paper
That was the same side zone.
Yeah,
The
it's the
axial
same
and
side
side zone
zone.
issue was exactly.
But again, there wasn't a model that has 5 bar messengers.
Yeah,
So I don't think it's
The one that
Yeah,
generates
yeah.
the mutant.
Yeah.
Then it doesn't solve it. Just hypothetical problem. Because then
Sure.
you have to break
So-
these,
You have this model with gauge-mediated SUSY breaking. So you have non-universal, you have multiplets which are not in multiplets,
Yes.
but you also have hypercharged flux,
Yes.
and you
You're asking about
calculate
unification.
threshold corrections at the
Yes.
gut scale.
So what, I completely didn't discuss it, but what you study in detail is how actually you can still get something that's compatible with the weak, the coupling to the weak scale. So there are low scale threshold correction, high scale threshold corrections. In fact, those high scale ones will be relatively dependent on what kind of surfaces you're actually looking at. So those are put in actually as a parameter. So we scan through values of those and ask, is there a reasonable range so that they actually still are compatible with the gauge couplings that we measure? And yes, definitely. So, but that's all included because it's not clear. You'd have non-dot multiplets, you run them up, everything could happen, right?
And then you got the hypercharged flux, which is breaking.
That's right. So all these things added together, actually, in a very sort of way, and also two loop corrections. So it's yeah.
Just a comment. Why not giving up the idea of Pechet-Quinn symmetries and
Yeah,
giving
sure.
with B minus L, and then dimension 5 proton decay operators can be suppressed, as Eran told us, and I think
He
you
was
don't
also using PQ symmetry.
PQ. What? No,
Where
B
is
minus L. No, you don't use.
But yeah, at some point he also had PQ symmetries.
No,
So-
you don't need it.
Okay.
For dimension 5, you don't. I mean, dimension 5 operators are not terribly dangerous. I mean, it's very easy to suppress them.
Well, but the dimension 5 operators are invariant of the B minus L.
Yeah, it's true. No, it's not B minus L. No, B minus L is for dimension 4.
Right.
Yeah,
No,
so that
dimension
one is
5 are
not
suppressed
useful.
because of the wave functions effects. That's what Eran was telling
Yes,
you. You don't need
so-
a Pechet-Quinn there.
Yes, so I would actually like to see how wave function effects will work in this kind of context before. I mean, that's definitely a valid thing you can do. But
And
I would like
avoid
to do
exotic
something. So
effects.
this is a framework where I'm saying I look at PQU1 symmetries. They solve a lot of issues. In particular, they solve the mu problem, engagement mediation, also the dimension 5 proton decay. In that framework, this is the conclusion. I agree. One should also study what are the other options. But I think it's at this moment difficult in, say, this Calabi-Yau context to really study this wave function stuff. It's a little
Sure.
big.
And just a comment, so the cosmological moduli problem is quite an old one. I mean, one of the organisers
I know, no.
has
So-
made it quite a while ago.
Yes. Of course, but it's in this, like this small part paper that they have, the argument seems extremely streamlined, very sort of general. And it would be interesting to actually know what happens.
I disagree with that. The cosmological model problem is completely general.
It's
More than,
right,
more than
okay.
15 years ago.
Okay, fine. So 15 years ago, I was working at ADC.
Yes, but then you have to get the proper credit and you do it afterwards. Anyway, so any more questions? Sure.
Yeah, you could also use discrete R symmetries to solve both of those.
Yes,
mu
you
problem.
can, and that was
can
one
you
of
do
the,
that?
well, that was one of the points here. So, I mean, you can either do discrete symmetries, but that again will depend on the specifics of your geometry, or what you are doing, Wilson line breaking, that also gets rid of the hypercharge, but I guess that's also very model dependent. Right, so that, in that sense, I like the PQ symmetry thing because it's not constraining the geometry. It's a very general kind of setup.
Okay, let's thank the secretary.